This is the second video for tests of proportion problems, and we're going to do problem number 2. So let me just go right to the text of the problem. And we see that the problem is a government bureau claims that 67% of tax returns were filed electronically last year. A random sample of 144 tax returns from last year was examined. Of these, 59% were filed electronically. Test the government bureau's claim at the alpha equals 0.05 level. So the claim is that 67% of tax returns were filed electronically. So the 67% implies that this is a proportion. The value is going to be 0.67, and the relationship, it says, claims that they were filed electronically, which implies that the proportion was equal to 67%. So the claim is going to be that P equals 0.67. And then we've got alpha is 0.05. And in the information in the sample, highlighted in blue here, we have 144 returns, which is the number of trials, and 59%, which is the proportion of the trials in the sample. So 59% is P hat, okay? Do not get these two things confused. 67% is a claim, that means it's P. 59% is talking about sample, that means it is P hat. All right, so the problem, we know how to go through and do our setup for our hypotheses, etc. We need to note, however, that in H1, this is not equal, which means it's a two-tailed test. And then we are going to now have to find the test statistic value. But since we know it's a test of proportion, we know the test statistic formula is Z, and we know we need to know what P hat is and N is, and we got those things from the problem. P hat is 0.59, and N was 144. P, again, is 0.67. So, and Q is going to be 1 minus that, or 0.33. So we calculate our test statistic, okay? Then we're going to look at the critical value approach. And the critical value approach, if you recall from the last video, is we're going to find critical values using inverse norm. And inverse norm requires that we put a less than probability into that function. So we need to, for each critical value, we need to know what the area to the left of that critical value is going to be. And that depends upon alpha. Alpha is 0.05. So let's go ahead and let's define what that alpha is for the left one. Remember, alpha is 0.05. That's the total alpha. We're going to be using half of alpha for the left critical value, and 1 minus half of alpha. The area to the left of the right critical value is going to be 1 minus half of alpha. Okay. So we're going to be putting those two things into our function. So let's go find the function, and we end up with, let's quit out of here. And remember, this function, inverse norm, is under second vars, and it is number 3. So we need to, and remember, we're looking for the left one now. And since it's a two-tailed test, half of alpha is going to be in this tail, which means that the area to the left of this critical value is going to be 0.025. So let's put 0.025 in there. Close that and hit enter. And we get negative 1.96, which is what we'd expect. It's one of, since alpha is 0.05, two-tailed test, we need to remember 1.96 for the right tail and negative 1.96 for the left. Let's double check and make sure that that is what we'll get on the left. We'll run this one more time. Second vars 3. And we need 1 minus the area to the right of the right critical value is 0.025. 1 minus that is 0.975. 0.975, close parenthesis, and we end up with positive 1.96. So we've got our, we can use a calculator, the inverse norm function, to find critical values. So let's stop here, go back to the problem. And now let's look at, and remember what you're going to do. You're going to plot draw this little curve with the line for the z and the curve above the line, and mark in the critical values, negative 1.96, positive 1.96, and plot the test statistic and see where it falls. It falls, oops, sorry. It falls to the left of the left critical value. Therefore, it's going to be an unlikely test statistic value. Let's then look at the p-value approach. Okay, so p-values, this is a two-tailed test. So this is kind of a special situation. In two-tailed tests, we're going to, for the p-value, we're going to basically, if we draw a picture, we'll plot the test statistic, and we will find the area underneath the curve, farther from the mean than the given test statistic. So that means the area in the tail to the left of negative 2.04. But that is only going to be half of the p-value. Because it's a two-tailed test, values of the test statistic farther from the mean than negative 2.04. And by farther from the mean, we're just talking distance, not necessarily direction, but distance. There are values of the test statistic that are more than that distance away on the right. They would be out in the right tail. So we would have to find the area in both tails, but we're going to just look in the tail where the test statistic is and find the area farther from the curve or mean underneath the curve from the test statistic, and we'll multiply it by 2. So that means we're going to first find that area to the left of negative 2.04, since the test statistic is on the left, and then we'll multiply it by 2. So let's go find our there, and let's clear this. And remember, to find the normal CDF, we're going to go second, vars, number 2. And now we want the area to the left. I'm sorry, normal CDF requires that we have a lower bound and an upper bound. Since we're finding the area to the left, we're going to go from negative infinity up to the test statistic. And negative infinity, we're going to use instead a large negative number and then a comma. And then the test statistic, negative 2.0, I believe it was 4. Let me take a quick peek and see. Yes, 2.04. And then close the parenthesis and hit enter. There's the area to the left of the test statistic value. But this is a two-tailed test. So we need to multiply this, our previous answer here, times 2. And there is the p-value, okay? This is not the p-value. Two-tailed tests, we only found an area on one side. We have to multiply it by 2 to get the total area. And there it is, 0.0414. Okay, stop share and go back here. All right. Then remember what we do with the p-value. We compare it to alpha. If it is less than or equal to alpha, we'll end up rejecting. If it is greater than alpha, we'll end up failing to reject. This is greater than alpha, I'm sorry, less than or it's less than alpha, so we're going to reject. And also negative 2.04 was farther from the left critical value, which would cause us to reject as well. And then we make our statement of conclusion based on the flow chart in the table, in the handout that you have. Then we can run the test. Remember what the test does, the one prop Z test for test of proportion. The one prop Z test basically answers the question in step 2, what's the value of the test statistic? And it answers the question in step 3, what is the p-value? It ignores critical values entirely. It just answers those 2 things. Okay, so let's do this. Let's go ahead and take the information we have. We had that, well, one thing that it requires is it requires a value of X. We weren't given a value of X in this problem. So we had to take the p hat that we were given and multiply that times n to get and round it to the nearest whole number to get a value for X. So 85 and 144 are what we're going to be putting in there. So let's go back and do this on the calculator. Share. Okay, so let's clear this and let's go to stat, right arrow to tests, and number 5 is the one prop Z test. Remember, number 5 is the one prop Z test for test of proportion. 0.67, as I recall, is our 0.67. Enter, and 85 was our number of successes, and 144 was our number of trials, and it was a two-tailed test, so not equal should be selected. And then we go down to calculate, and we get our test statistic, negative 2.034. Now, notice here that this is slightly different than what we ended up with by calculating it by hand. And the reason that it's slightly different is when we put stuff into the formula for the test statistic, we used p hat as 0.59, which is correct. That was given to us. But when we put the information into this, we had to put an X in. So we had to find X using p hat times n and then rounding it. So this is slightly different because what we put into this one prop Z test was a rounded value for X. That's what made this different. And again, same here, the p-value 0.0419. That's not quite the same as what we had when we did this by hand, because again, we used a rounded value for X. All right, so let's get out of here and go back to our problem. And that gives us basically the same results. Instead of, we had a slightly different p-value and we had a slightly different test statistic, but we're still making those same comparisons, and they're not far enough different that it changed our decision to reject. And then we would still have the same statement of conclusion. So I'm going to go ahead and stop here, and we'll pick up with a third example. And so we'll leave it at that for this video.